Okay, so, well, I thought, how could I give a talk in 5 minutes about my past work? So I thought I'd rather start by giving just a phrase about my past work and concentrating on the future, and making this, rather than an exposition of my work, a call for action. So, sea ice. Sea ice is cool. Well, during my PhD, I've recently discovered that many of the things that I've been doing are related with one particular topic, and this is sea ice. That's why I'm going to talk about that. So, for understanding how the layers of ice in the ocean form and how do they evolve over time, we need to understand their fractal structure or their large-scale shape. And I think this could be related with something in my thesis called smooth sets, well, not invented by me. And also the microscale structure of ice is related with signal processing and random matrices, and this is connected with the other two topics that I've studied in my thesis. So, so I've recently been in a talk where the speaker presented some computations about the roughness of the shape of the ice layers in the Antarctic Sea, in the Antarctic Ocean, and so I want to know more about this. So climate is important. I guess that everybody will understand that, but it seems necessary to explain it, predict it, and control it, and in particular to predict temperature. And so temperature of the Earth is explained by many factors. The main one being the intensity of sunlight received, but also the atmospheric composition, the water currents, and the one that affects us in this case is the albedo. That is the percentage of sunlight that is reflected by the surface of the Earth. Many of you may know this, but the darker the color, the more light we absorb. So, for example, white color will make more sunlight get into the Earth. And so the biggest component of change in the color of the Earth is whether we have ice or no ice over the oceans near the poles. So understanding this shape is important. Sea ice is wild. So the large-scale structure of the layer of ice is a very wild fractal. This can be measured in the way that, wildness, the intuition of wildness is defined as dimension. This can be measured in a classical way, and it can be measured that the large-scale structure of sea ice has a dimension close to 2. Classical regions that one can imagine have dimension 1, and typical coastlines are around 1.3 or so. And so this is in the hypothesis that I want to check is based upon the fact that when you go from the interior, from a big layer of ice to a big layer of ocean, you don't all of a sudden appear on one place to the other, but you go through a very smooth transition between the two states. So my hypothesis is that the key driver of this dimension being 2 is contact, diffusion of heat. So that the important thing is that the heat transfer between nearby layers of ice, and not so much because of atmospheric or current or water currents transfer. And experimental data only contradicts this on small scales, less than 1 kilometer, and it verifies this on larger than that, where water currents could have a more leading role, reducing the dimension. So I need you for this. I need help because I am not a physicist, and I need to, I think it's a topic where we need to understand better the dynamics of water and heat processes involved. And I want to study a problem that is with some contour conditions and some initial conditions that reflect the wildness already. We want to study the set of the places where the temperature is bigger than 0 at a given time, and its evolution over time. And I want to know what happens with this set when t tends to infinity, when the time tends to infinity. Does it converge to anything? In which sense? And making simulations of this. And when I put heat and temperature, we could also be thinking about osmotic pressure and concentration of salt in water. So if you happen to know about this, please talk to me. Thank you.